I'm excited. What was our other partner's name again? Gage.
Well, thanks for coming again. I think instead of, or due to the superposition of feelings towards your presentation, you're still in the class. I want to take it as a credit that you like the class, but maybe it's just because it is a requirement. So, who we are and what are we doing? It's right question to ask after. Well, I've heard this thing 2 times. First, in the course of economics and business in my undergraduate, which okay, pose the goals. And second, there is natural thoughts of a person after a hangover. But it's the third time when we can practice it is here in the class. I think you don't mind. So we are in the physical chemistry class, and we all impatiently wait until you can predict outcome of measurements in some experiments, like spectra, NMR, activation barriers, and we are suffering boring mathematical exercises for a long time, and we will to continue for the most of the class. So in this mathematical exercises, what is a connection to physical chemistry and what is our tactical goals? How do we wrap up what we are doing? So we are looking on stability and processes in molecules which cannot be described without electrons, which have some wave nature. And we need equations that describe what electrons are doing, and second, ways to solve them. Right? Since electrons are so vivid that they do not stay still most of the time, we are not happy with just static equations and solutions. We need to look into the time development. And in the oversimplified language, we can tell that our goal is to predict future. Predict future in the sense of electrons. So by now we do, well, of course, you are certified experts in many things, including postulates of quantum mechanics, but in the regular narration of the course, we do have 2 ways to predict future of electron. First, by what?
Evolution operator.
Yes, wave function evolution operator. And second is by infinitesimal increments, propagating forward in time, which works well for numerical volume. And now we are looking to conclude the third method to predict future, which is most practical, most powerful, and we will practice it at least 5 times during the course. 5 times is not like solving problem of 10 minutes, it's 5 big times. So the third method will be based on separation of variables and solving Schrödinger equation in a standard way how people solve differential equations. One separates variables, one finds general solutions, and then one constructs partial solution as superposition of general solutions. Linear combination. Sounds like this. And we will go through this way which some of you may experience in differential equations. Or if you didn't do this course, we will cover the basics sufficient for our course. And by the end of today's meeting, I will ask for your opinion. Would you prefer white background or black background? So it is a place where we stopped last time, right? And after presenting on the postulate of quantum mechanics, nothing in this long list looks like a surprise. So this is an equation that we want to solve, right? So we want to know wave function of an electron at each space at any time. And it can be reduced to a time-independent equation that gives set of eigenvalues and eigenfunctions that are proper eigenvalues of this energy operator, Hamiltonian. What else? Good solutions of such equations should match so-called orthogonality condition. And then we want to use this information as a building blocks to solve this equation. Okay? And I promise that by the end of today's meeting, we will have. So, in some sense, it is our last pure methodological meeting. From next meeting, we will go into applications. They will be very ridiculous, inapplicable to real life, or very barely applicable. I can disclose the secret. We will consider a universe consisting of one electron for like 4 meetings. But otherwise, it will be only fairy tales without any practical. You will not develop skills to do anything useful for your career. So you better go slowly but surely. What's special about energy, based on your experience in the class? Just give any ideas. So, and you can do tricks and know about my interest profile and focus. If we are looking on time evolution, and we spend so much time about phase accumulation and action in the exponential. So, in this aspect, why do we need energy? What is useful in knowing energy of quantum states of the system? Yes.
I mean, it helps us like make predictions of what's going on with the electron. Gives us some kind of like quantifiable data of where it could be or what its movements are like.
Yes, it is correct, but very general. Let me start going into more specific. So when we were going from time-dependent to time-independent Schrödinger equation, we guessed the solution in the form of function that depends on x times we were calling this thing a constant, but through some tricks we immediately discovered that the energy of an electron, it is what helps it to evolve in time, to accumulate phase. So as time passes by, electron getting more and more phase. Okay? So the energy is good because energy of orbitals, energy of quantum states, not the total energy of system. Energy of states is good because we learn more about states, and if it is molecular orbitals, we can know something about electronic properties in static case. But in the perspective to time development, each energy is a key factor for accumulating phase. So if you look into predicting future, we need energy. So what is special about energy is that it sets up time evolution. Evolution and phase accumulation. in very narrow sense, this is already prediction of the future and solution of time-dependent Schrödinger equation, right? We have product of space part, time part, and here we can put x. This is correct, but very boring. I know everything in the course is boring, but it is especially boring because it is trivial. It doesn't tell us anything, so nothing changes in fact. So it's just a factor to this function. And it is prediction of the future, but very boring future, when the past and future do not change much. Here I'm going to lie. But in the frames of this course, it is correct statement. But generally, it is a big lie of quantum mechanics. A state if system is prepared in the eigenstate, it will stay there forever. So if we are in the eigenstate, this phase evolution will not break this eigenstate. System will stay there. No measurements, no any collisions. Therefore, it is boring. You are allowed to yell now because it is boring. But we want to look onto non-boring situations. And before we look on this, let's focus on the requirement of orthogonality in the properties of eigenstates, eigen-functions of time-independent Schrödinger equation. Please give me a sign if the word orthogonality makes you happy. Okay, I saw something. Give me a sense if the word orthogonality makes you very unhappy or a little bit unhappy. So, give me a sense if you hear it for the first time. Okay, good. So, we are not mathematicians. Therefore, we try to minimize amount of math to minimal level, but we cannot do without it. So, all eigenfunctions of Schrödinger equation should satisfy this equation. If you multiply function by itself and integrate, it should give either 1 or 0, depending on if you multiply it by itself or function with different number. What is it? How to understand it from common sense? Let's draw a simple function which will be just 1 everywhere. X. So function 1 equals 1. Now function 2 equals x. And now our infinity will be equal to L capital. So suppose that we do this operation. We have 2 of 1 dx integral. What are we going to get? So give me answer by fingers. One more try. One more try. Okay, one out of 14 was correct. So when you multiply 1 by x, you get x, right? And you integrate on the equal amount of equal range from negative and positive, right? So you measure, the integration is measured under the curve. If you measure area of this triangle with sign minus and area of this triangle with sign plus. So they are of the same height, same base, but different signs, and add them together. What will be the answer? Yes. Good. So you hopefully get a feeling of orthogonality. So such functions multiplying each other, multiplying them together, and integrating, you get 0. And there is also normalization, but it's too boring. We'll do it later. Anyone is not happy with orthogonality property now? Okay, suppose that we are happy. We need it because we will use it through the rest of our meeting. And this is not true time after beginning. Probably we started about 5 minutes later. So I should be very careful with time. What does it mean, past? In sense of our course.
Negative time.
Yeah, you can set it negative or time equals 0, but what does it mean past in relation to wave function? Can we say that past will always consist of eigenstate of the system? No, past can consist of eigenstate of eigensystem, but one eigenstate, another eigenstate, or superposition of them. So we need to introduce a methodology, an approach that will accept any past, any initial condition, any general situation. So if we project from past to the future, we should not restrict ourselves to specific cases of past. So any past, any shape, any type of function that we accept as our initial condition at time 0 or time minus infinity, whatever you prefer, should work. So this is main idea, and the rest will be just boring math. Bless you. We kind of get through here. So solution of time dependent is solution of time independent times phase accumulation, right? And we do get functions and energies. But our goal is to use all the ground that we got in order to find evolution in time, the propagation, the change in time of any wave function. So for this initial wave function psi, we understand that it doesn't need to coincide with any of the eigen-functions. So there should be no restrictions except that it should be normalized, it should be good function in mathematical sense. Like it shouldn't have too much of singularities or spikes or discontinuities, but it should be a very broad range of functions. Anything that can relate to initial condition of an electron. Like electron spread over around a nuclei, or electron spread over molecule, or electron running from one wall to another wall of a tiny nanomaterial, something like this. General. Help me, what should we do if we solve a differential equation and want to find particular solution matching given initial condition? So the key idea, superposition, means we are going to represent our evolution not by one term like this, but adding together terms like this for all eigenstates. So I'm going to place a summation sign, somewhere in this slide. Where should I put it? Okay. Or I can put it here. I can put some indices. We are done. Just kidding. We need to do a little bit more. So if I blindly, it's not just blindly, it's worse or worse. If I do a silly thing and just put summation sign, it will not work. Because if I just add them together, it means each of the eigenstates will contribute equally to the solution. But it is too wild approximation. Then if our initial condition, for example, consists only of one eigenstate and not others, then we should skip them from the summation. So we need to have some weights coefficients. So we need to allow each of eigenstate contribute to solution at different measure, with different expansion coefficients, with different weights. If you can reformulate this statement in your own words, you may write it down. So eigenstates contribute to solution of time-dependent Schroedinger equation with each of them contributes with its own weight. And our goal is to find connection between this weight, which we can put CK capital. And our goal is to find connection between this weight coefficients and the initial condition. Find connection of weight coefficients C sub k and initial condition psi x comma time equals 0. We are very close to the answer, and some of you are aware of the answer. I just offer very slow steps to see the logic, because it is one of the what we get by the end of today's class will be our main tool for the rest of the course. You use it again and again, and it would be nice to have the best possible understanding. So do not be scared. It's not too many symbols. Through the course, we will have much more busy slides. If it makes you picture. So I haven't made anything. I just reformulated what we had on the previous slide. So our solution, particular solution for specific initial condition is constructed as a superposition of space-time, time evolution, which are specific for each eigenstate, and this weight coefficients, or we can call them expansion coefficients, or I don't care how you call them. That's the answer. But it's not the whole story, because we do not know the values of these expansion coefficients. Even if you do know the solutions, if you know eigenstates and eigenenergies, we do not know these expansion coefficients, and we need to find them. We need, well, we are not, you can immediately object me and tell, no, you are wrong. We cannot find any expansion coefficients because we are not solving any specific problem. Right? Once a friend of mine was doing a practice teaching in the middle school, science for middle school, and was administering a lab with, it was not a lab, it was just a little short exam, quiz. And the assignment was, suppose, it was very introductory science with density or whatever. Suppose you have a wooden brick of this length, height, find the density. And everyone in class starts writing, and one person was sitting and doing nothing. He was coming. Why are you doing nothing? I'm supposed to get a brick. So, like, where is the brick? It is written. So, you can make the same objection right now, that we are not solving specific problem. How can we find exponential coefficients? Well, we need to establish a protocol, lab protocol, how to find this exponential coefficients. And then we will be in a good standing. So we need to connect these exponential coefficients with what? With which conditions? We need to find connection with initial what? Okay, I think we got it. With initial conditions. How? What does it mean, initial conditions?
What's that?
Yes. London?
Yeah.
You did answer what are initial conditions for wave function. How did you? Can you repeat? You answered like it is wave function at negative time,
Yeah.
or we can accept it wave function at time 0.
Yeah.
Right?
Yeah. So you plug in 0 for the time and
Yes.
figure it out from there.
Correct. So here we take our functional form, our hypothesis of solution, and we plug in, instead of time, we plug in 0. What has changed? What is the exponential of 0? Now you'll catch it. Exponential of 0 is 1. No objections. Therefore, we get rid of this time dependence, and we have on one side definition of initial state according to London. So wave function at time 0, right? On the left. And on the right, you have same as we had before, but without time dependence. Summation with exponential coefficients and eigen-functions. What do we need? We need to find these coefficients and get rid of the functions. We need to do something to this expression to focus, to get answer for this C sub k. So which first practical thing we discussed at the beginning of the class?
Orthogonality.
Orthogonality. So orthogonality is something that will help us to simplify this expression. Maybe not making it shorter, but make it more practical, useful. So we do have this psi x0 equals summation k c sub k phi sub k x. And we feel that orthogonality will help. So why don't we do a little numerical experiment and multiply each term from each side, from left and right, by eigenfunction with little star with different index. If here we had index k, here we put m, and we can put somewhere here dx. So it will be operation of integration. Integral dx phi star over n. What are your expectations? What should it give to us? Well, some of you are smiling, and I see that I see the answer in your eyes. But who doesn't know answer and can just hypothesize? What does this expression promises us? Do you see any simplification? So let's look back. Let's focus back on the orthogonality. What is it?
It's like basically it's squared function.
So
wouldn't this come out to equal 0 as well, since
orthogonality is a procedure that converts complicated functions into simple numbers. 0, 1, whatever. But the main idea that function is if you do Excel and you want to represent function numerically, you have so many numbers to show the line. And you have two functions. So the orthogonality is a procedure that takes two functions and converts them into one number. So there is a hope that if you take these two functions and consider them in a sense of orthogonality, you will get rid of them. And there will be no functions, only numbers. Numbers are always better because they're simple. So we expect to get rid of functions. So it's our main expectation. Yeah, nothing new. You saw it. K dx. What is it equal to, according to our agreement?
1 if k equals n, 0 otherwise.
K 0 is not equal 0. Do you believe that here we are in class are so advanced intellectually that we are the first in the world who do it? Well, I wish, but unfortunately not. Do you have an idea about names of scientists who dealt with orthogonality in application to quantum theory?
Griffiths refers to this thing as Fourier's trick. I don't know if he actually had anything to do with it.
Huh?
Griffiths talks about Fourier's trick, like this thing being Fourier's trick.
Yeah, but just one name.
Hilbert?
No?
Banach?
Huh?
Banach?
No? Any names you heard in connection with quantum theory?
Einstein?
Good, but no.
Rutherford?
No.
Fine.
No.
Schrodinger?
No.
We're just yelling out names now. Like random names here.
Heisenberg? I don't know.
No, but you're making the list shorter and shorter. So,
Oh, dear. Right.
so
Right. There's just too many names.
what he suggested, well, he suggested many things. But why don't we replace this long and boring expression just by a symbol delta and k, which will be defined the same way. Just because sometimes we need to perform summation over this, and delta is more comfortable than the large bracket and two-store building. Okay, so Dirac delta, which means it is just either 0 or 1, depending on how the indexes are behaving. Dirac delta.
Wait, that's the Kronecker delta, isn't it? Because Dirac's delta is the integral.
Oh, I'm wrong. Yes, you're right. So it's not Dirac, it's Kronecker. Good. Extra credit. So I just swapped the order so that the C sub k doesn't disturb us from focusing on this orthogonality. From top to bottom, I just swapped the C goes to the front, and these two things go to here. And then we replace this box with just symbol delta and k. We are almost ready to give the answer and analyze it. But just before, tell me what these two symbols make to each other, if they meet. I'll tell you. So this is a little hungry, angry snake.
That's the little mouse.
And this is a little rabbit with ears. So the snake eats rabbit. So if the summation sign meets delta sign, nothing is left. They just cancel each other. Okay, now a little bit more scientifically, same idea. So here is our snake, here is our rabbit. So this delta function, which it means like either 0 or 1. So if we summation means that we scan through possible values of this variable k. So k equals 1, k equals blah blah blah, k equals n, k equals bigger than n. And depending on the match between these values, our delta function is 0, 0, 1, 0, right? But if you make summation of a long string where all terms are zeros and only one is 1, what will be the answer?
1.
Yes. So it is how snake eats a rabbit. Now, here is some appropriate word. Delta. If we have not just delta, but delta multiplied by some progression, some discrete function, what is the answer? So same ideology. Summation means it is a row of many terms. K equals 1, k less than n, k equals n, blah, blah, blah. And each term is something left over from delta function, which is 0, 0, 1, 0, and actual discrete function. C1, Cn, 1, Cn, Cn plus 1. But the factor is equals 1 only in front or after one of these terms. All the rest are multiplied by 0 and eliminated. So the summation in delta pick one term in progression. Okay. Now, how do we deal with it? What do we have? So on the left we had phi n star psi initial condition according to random dx equals summation of c sub k delta and k. Right? Due to orthogonality. So with your new knowledge in math and progressions, how we can simplify this notation? It is equal to
CK.
c sub k. But we can read it in the different direction. C sub k equals integral of initial wave functions times one of the eigen-functions and integrate over the whole space from minus infinity to plus infinity. So, hurrah, hallelujah. We got the answer. We know how to carefully treat the past. We know how to find weights. We know how to find expansion coefficients that contribute to solution. In fact, by now we do have the third way to predict future. So for any function of the past, we multiply it by each of the available eigenstates, integrate, and record the answer. And this set of such coefficients for each of the eigenfunctions should be n, because k was removed during summation. So we do have set of this set of C sub n, right? Very good. So convolution of eigenfunction with initial condition. If you want to sound smart, you can replace the word integration by the word convolution. And that equals to expansion coefficients. Here it is. Well, I can scroll it back and rewrite it if you like my calligraphy. But I'll probably do it because you better write it in your notebooks to help a little exercise of memorization. So wave function at time t is summation of the expansion coefficients wave eigenstates, eigenfunction, times accumulation of phase, where the expansion coefficients are found as convolution of the initial wave function x, 0. Oh, here is t, here is 0, times phi sub k dx. This is prescription. This is protocol, lab procedure, like manual, how to predict future. No, it works. You will see that it works. We just do not look on specific problems to save time. Otherwise, it will be too long for our already short meetings. So, summary. First way, psi of xt equals psi of x0 times evolution operator. Second way, psi of xt plus delta t equals 1 minus I h bar h delta t times psi xt, right? Second way, numerical. Depends on delta t. For delta t equals 0, there is no change. And the third way, I'm just lazy to type because I just did it. So 3 ways to go from past to the future. Past, future, evolution operator. Past, future, infinitesimal evolution operator for numerical modeling. And the best of the best, method based on solution of eigenstates of time-independent Schrödinger equation allows them to be used as building blocks to find time-dependent solution. So summation of eigenstates with phase accumulation and with expansion coefficient that are found as convolution with initial condition. So this is past, this is future. Any questions? If no, let's finish the meeting. Looking forward to see you on Wednesday, same place, same time.